All right, everybody. Sorry I'm a little bit late. The exams were quite good. I was very pleased. If you have questions, I'm going to be having office hours right after this class, as always, but I'm going to have them in this room. And the first thing I'm going to do is I'm going to quickly go through the problems of the exam. There are some problems that a number of you had trouble with. Most people had trouble with. Problem number 5, which was a book example and a recitation problem and a homework problem. Bummer about that one. So we'll be going over that one. All right, so I'm not going to go over it in class. So I'm going to start today's meeting. Meeting part 1 is a review of what we did on Monday. Monday we were discussing signed area. We are interested in this weird thing, the signed area between a graph of a function and the x-axis, from x equals a to x equals b. We don't have a definition of what signed area even means, and we didn't have a definition of a way to compute it. But we thought about approximating it. So we approximated SA using rectangles. So the way that picture looked was the same picture. Now I'm going to draw just a couple of rectangles. So here's the first rectangle. And over here at the very end was the nth rectangle. And then kind of a representative rectangle in the middle could look like this maybe. So we're adding up areas of regions like that. Now we were interested in, we needed some things that we could compute. So we defined the rectangle width was delta x, and it's b minus a over n. And if we think about the interval with the rectangles, it starts with the number a, and it goes over to the number b, way over here. Now we define this number to be x subscript 0. And then we went over a distance delta x to get to what we call x subscript 1. You could say x sub 1. The subscript 1 is just to keep track of which one you're talking about. I'd like to not see cell phones, and I don't mean like in your lap. I mean like please put them in your backpacks. I really don't want to see cell phones. So, and then we go over another delta x to get to what's called x2. So for instance, x1 is a plus delta x. x2 is a plus 2 delta x. Now we go on like this. This is the second to the last one, x subscript n minus 1. Now the last one is supposed to be called xn. Well, let's see what the pattern is. If I do that all the way to the end, x subscript n should be a plus n delta x. Oh, but we know what delta x is. It's that thing. So x subscript n is a plus n times b minus a over n. Oh, and look at that. The n's cancel. So I get a plus b minus a. Oh, and look at that. Those a's cancel with my pumpkin spice chalk, and I'm left with b. So sure enough, my last x value is x subscript n, which is the same as the number b. So remember that these little pieces of real estate were the pieces of real estate where we sat our rectangles. And we sat n of them there. And when we built our left rectangles, they're n left rectangles, and they're all touching the graphs at the rectangle's left edges. So we used those were the x values where those left rectangles were touching the graph. When we put right rectangles on, they're sitting on the same piece of real estate, but they're touching the graph at these x values. So the right rectangles used x1 to xn, did not use x0. The left rectangles used x0 to xn minus 1, but did not use xn. Either way, there are n x values in that list. In the whole list, there's n plus 1 x values, starting with x0, ending with xn. But in each of the sums, the left sum, we use this batch of n. So these were used in ln. And this batch of ones was used in r subscript n. All right, now, I should have put that on the sideboard, sorry. I want to project the results from, again, this is all from Monday. This is all review. So on the web page for today, review of notation and definitions. So there's our definition of the rectangle width. Here's the list of important x values. And then here are our sums. Here's the sum for Ln. It's the sum of the areas of n rectangles. 1, 2, all the way up to the nth one. Starting with x0, ending with xn minus 1. Each of these things is a rectangle width, so it's a rectangle area. So it's a width and a height. The height of the graph above that point. This rectangle's height is the height of the graph above that point, above that x value, and so forth. Now for the right sum, again, we have n rectangles. So the areas they're n areas. Each one is a width and a height. Width and a height. N of these terms, each is a width and a height. They're all the same width, and the heights are obtained from whatever the height of the graph is above the right edges of each of those intervals. So starting with x1, x2, up to xn. Those are all the ones that got flagged with a red arrow. So we had those sums, those lists on Monday. Now you encountered this notation in recitation yesterday. It's also in the book, and you'll see this a lot in your science classes. This is an abbreviation of that, but you also need to realize that this is also an abbreviation already, because I don't know what n is, so I don't have the whole list here. So this notation is telling us, well, you've seen enough to infer a pattern. Keep doing that and end when you get to this one. Here, you've seen enough to infer a pattern. Keep doing that until you get to this one and stop there. Now, do you know what the name of this symbol is? Until I was like 60, I just called this ... But then I learned that there's a name for this. Cooper knows it. He's going to lord it over us unless somebody else gets their hand up. Yeah. Yes. Was that what you were going to say? So this is an abbreviation using using this ellipses, which I really prefer ... because if you use the word ellipsis in a conversation with most people, they're not going to know what you're talking about. So ... What?
I just thought it was called an ellipse.
No, that's the other thing. That's this thing. Now, how is this an abbreviation of that? Well, notice this is a bunch of things added together which all look the same. A width and a height, width and a height. So this symbol tells you the same thing. Add a bunch of things together. So this is supposed to evoke summation. It's the Greek letter sigma, capital sigma, to evoke the S. And it's saying add up a bunch of these things, width and height. So this is a rectangle area for one of those rectangles. This could be like the generic rectangle in the middle. This could be like the ith rectangle. And this is saying beginning with the rectangle that has I equals 0 and ending with the rectangle that has I equals n minus 1. So that's an abbreviation for this exact list. Starting with the rectangle that has I equals 0, ending with the rectangle that has I equals n minus 1. Same thing for the right sum. This symbol says add up a bunch of things that look like this, beginning with that one, that's that one, and ending with that one, that's that one. So the summation notation is meant to be your friend. All right, now, let's go on stuff we did on Monday. We defined signed area. Remember, we didn't know what it meant. We didn't know how to compute it. By the end of the hour, we had both those things answered. This is what it means, and this is how you compute it. Signed area means this. So in other words, you build the generic sum where you don't have n specified, and then you imagine what happens when n gets bigger and bigger and bigger. Imagine what happens when you use more and more rectangles. So that's the definition of signed area. We had that on Monday. Now, using this fancy summation notation, we can notice how this is a bit more concise. So here is the expression for Rn. Here I've parked the limit in front of it, so this much of it is an approximation of the area. When I do this, that's turning it into the exact signed area. And this is the symbol for it. So that's Monday. All right, well, so that's meeting part 1. Meeting part 2 is now section 5.2. We're going to introduce the definite integral. So this is section 5.2. So here's a definition. First of all, a really cool new symbol. It's a thing that looks kind of like a big S, because it is. It's a big S. And at the bottom of it, you have a decoration, x equals a, and above it, there's the decoration, x equals b. And then to the right of it, you have f parentheses x, and then next to that is a dx. And this is spoken the definite integral of f of x from x equals a to x equals b. Notice I don't say the definite integral of f of x dx. You don't speak the dx. The dx is kind of the frame. Like this stuff on the outside is the frame. This thing on the inside, the Chewy center, is what's called the integrand. You say you're taking the definite integral of f of x. And the meaning is the signed area. Between f and the x-axis. So the signed area between f of x and the x-axis from x equals a to x equals b. So we've already got a symbol for that. That's the thing that's on the board over there. So that is this new symbol and this new term, the definite integral of f of x from x equals a to x equals b. That just stands for this thing. The limit of the summation starting with I equals 1, ending with I equals n of f of x subscript I delta x. So in math, there's a lot of really hard calculations. And there's also a whole bunch of notation and terminology. And it's always helpful to acknowledge So it's useful to acknowledge that there are two different projects. One is learn how to do the hard calculations, and the other thing is learn how to read and write these and recognize this hard notation and all this new terminology. So there's a lot to internalize here, a lot of new terminology and symbols. One thing that will help is if you get cranky and say, well, why is this the symbol? Why on earth use this weird S? Why do this? What's wrong with this? Well, for one thing, this is kind of cluttered. But also, remember a while ago I said, here's the symbol when I parked the LIM as n goes to infinity in front of Rn. But it doesn't have to look this way. I could also have parked this in front of Ln and I would have gotten the same result, but it would have looked different. The summation symbol would have looked different. So we don't want it to be that the different things that mean the same thing can look so different. So how is this supposed to help? Well, the idea is, remember on Monday when we had the computer making the sums with the rectangles, and we started using more and more sums, and this jagged region started to look curvy because the rectangles were so skinny you couldn't actually really see the individual rectangles anymore. It just kind of got smoothed out and it looked like the region. So that's the idea, that limiting process, imagining doing that as you use more and more rectangles. So this smoothed out S is supposed to remind you that this is the result of a limit process. The limit of this jagged S is the way I think of it. And this delta x, that's the rectangle width. When in the limiting process, well, it shows up here. This dx is supposed to remind you that in the original summation there's a delta x. Now, in the sciences, you'll hear people throw around jargon sometimes that it would drive me crazy. So one thing that I heard is, here the rectangles are infinitely skinny, which would drive me crazy because I don't know what the hell that means. Infinitely skinny. It doesn't help me at all. We know what limit means. You're taking the limit of this, and that's what this stands for. It doesn't help to say that the rectangle width is infinitely small. It's not. You're taking a limit. The limit of something that's finite, and then this symbol is to remind you that this is the result of taking a limit. All right, so there's the definition of, I made it through the day without losing my notes. There's the definition of the definite integral. So while we've got that definition up there, let's remember we've already done the definite integral, sort of, on Monday. So Monday's example, we had the graph of y equals 1 over x. And we started at x equals 1, and we ended with x equals 7. And we are interested in this signed area. So that's a symbol for a signed area, the signed area between the graph of 1 over x and the x-axis from 1 to 7. Now on Monday, we did this on a worksheet with 3 rectangles and we got an approximation. And then I fired up the computer and I started using more and more rectangles. Well, actually what I should do is I should say this. This thing, the symbol for this thing is the limit as n goes to infinity of the summation as I goes from 1 to n of f of xi delta x. We didn't use that notation on Monday, but we had this kind of notation. We were thinking about sums that look like that, and what we did on Monday, using a computer, we figured out that this is roughly 1.95. That's an approximate value. So for with our new symbol, we can write this. The integral from x equals 1 to x equals 7 of 1 over x. Again, you don't speak the dx. It's like, you know the word spelled O apostrophe possum? It's just possum. You don't pronounce the O. So this is just the integral of 1 over x. And we found out that it's roughly 1.95. So this is the approximate value, and this is the symbol for the exact thing. You might not like an approximation, but we can get a really good approximation by, we could have done like 1,000,000 rectangles. We could have gotten a lot of digits of accuracy here. Okay, so we've seen the definition of definite integral. We've actually seen that we've done one, at least approximately. So meeting part 3, I wanted to turn our attention to definite integrals using geometry. So for this, you should all be in pairs, wishing that you were in Paris. So pull out that worksheet. And remember, these worksheets are always available on the web page. If you miss class and you're watching this on the web, here's this worksheet. So these are examples of definite integrals where the graph is made up of basic geometric shapes. So remember, on Monday I started the discussion by saying you already knew some stuff about area. You knew how to find areas of geometric shapes using formulas from geometry. And then the quest was, well, can we come up with some theory of area that works more generally on curvy shapes? So we've got the theory now. But the question is, what happens if we use this notation and we look at examples where we could have actually done the area using geometry? So let's do that. I'm going to do this together. Oh, sign-in sheet. So I'm going to do the first one, and then I'm going to try to be quiet, which is always hard, and then I'll let you do some of the others. And then we'll talk again in a bit. I was so busy grading today that I didn't get to swim, so I have to exercise by getting some running in. So here we go. We have this worksheet, and our first problem is this symbol. Now we know what that means. It means the signed area between the graph of f and the x-axis, starting with x equals -6 and ending with x equals 1. Well, we can draw a picture of that. So first of all, let's shade the endpoints of this interval. So next, x equals -6 is there. X equals 1 is here. So on that interval, we have to shade the region between the graph and the x-axis. Well, I'm going to shade it in 2 colors. One is green. Think of the verdant green hills. And then the other is red, the lake of fire, below the x-axis. So let's look at these triangles. Notice this left triangle has a base of 2 and a height of 4. This red triangle has a base of 3 and a height of 2. I don't know if you can see that 2. And then this other green triangle has a base of 2 and a height of 2. So let's go down to the bottom, and for question A, the signed area is going to be that green area, which is 1/2 the base times the height, minus that red area, which is 1/2 its base times its height, plus that other green area, which is 1/2 the base times the height. And so this is 4, this is 2, and this is 1. So my signed area is 4 minus 1. Oh, 4 minus 3. Hello? Anybody awake? I need to give you all little bells that you can ding. So 4 minus 3 plus 2 gets me, the final answer is the number 1. There's my signed area. So a 1 goes in this cell. There's my calculation. All right, so now I'm going to try to shut up. Yeah?
Signed area is 3, not 1.
3, good, excellent. You really need bells. So the 3 goes here. You're going to all show your parents this video over Thanksgiving as evidence for why they should have me fired. All right, so I'm going to shut up and let you work on these, and we'll talk again in a few minutes. Is the sign-in sheet making it around? Yeah. Joe? Yeah. Can you see it now, Jonah? I don't know how to get rid of that little thing. These are the regions. What's the area? On the count of 3. 1, 2, 3.
0.
Wonderful. So you can have a signed area that's 0. This one, the region starts at -4 and goes to 1. What's the signed area in this case? You can have a negative signed area. Wonderful. -1. So this, the signed area is 0, and this, the signed area is -1. These numbers are the values of this symbol. This symbol stands for the number 0. This symbol stands for the number -1. Now, I'm going to turn the page over. I want to hurry us along here. The region from -5 to 5, I'm not going to do for you, but Chris kind of gave a spoiler a while ago. That region looks like this. There's this green area, there's this green region, there's this green rectangle, and there's this rock and semicircle. And then there's this triangle. So to figure that out, you're going to have to figure out the formula for the area of a circle, which Chris knows, and then you have to do the usual stuff. All right, who has an idea how to do E? The definite integral from 5 to 5.
Is it 0?
Yeah. Oh, you can't ask me that. You got to tell me.
It's 0.
It's 0. Because if you think about it, there's no area there. I mean, that's not really a region. So this one has an area of 0. So that's a property of definite integrals. If you have a definite integral where the lower endpoint, the lower limit is the same as the upper limit, that is automatically 0. You don't have to go through. In a couple of days, we're going to learn how to find the values of definite integrals. It's a lot of work. You don't want to go through that work if you know it's going to just turn out to be 0.
That's right.
Now, I want to end this part of the worksheet by puzzling over this one. Because when we talked about signed area, we talked about the area between the graph of a function on an interval like this. Here's the interval 1, 7. What's the interval here? Well, I'll tell you what it's not. It's not the interval 5, comma 1, because that's not a legal interval. You can't have an interval where the left endpoint is greater than the right endpoint. The interval from 5 to 1 is not a valid interval. So what the heck does this thing mean? This all started out with a function on an interval, but I've got something that doesn't have an interval associated to it. Cooper is anxious to answer. Anybody else got something to say? Cooper, take it away.
What if we multiplied it by -1?
Right, so what this means is this is defined to be, it means this, from x equals 1 to x equals 5, the integral, find that integral and then stick a minus sign in front of it. That thing does have a valid interval associated to it. It's the interval that starts with 1 and ends with 5. So this symbol, there is no interval that starts with 5 and ends with 1. So when you see this symbol, you have to realize first thing you got to do is turn it into something that we know how to deal with. So then you do the usual thing. You do the shading of the regions, you get the value of this, it'd be a number, you stick a negative sign in front of it, and that's how you get that. All right, so that's a whole bunch of examples so far of definite integrals cracked using geometry. Turn the page over, or turn to the next page, page 3. We're supposed to find this definite integral. Now for this definite integral, the region is from x equals 2 to x equals 8. And the integrand, the thing inside, is called the integrand. The function is y equals 1/2 x minus 2. Well, so the idea is we're just going to graph this thing, see how it looks, and compute our area, our assigned area, using geometry. So the graph of y equals 1/2 x minus 2 is going to have a y-intercept at 0, minus 2. It's going to have a slope of 1/2. So the slope m is the number 1/2. So if its slope is 1/2, then that means it's going to have an x-intercept here at 4, 0. Now our region is supposed to start at x equals 2 and end at x equals 8. I didn't really put my 2 in there here. I'll put my 2 over here. X equals 2, and it's supposed to end way over here at x equals 8. So my region is going to be this lake of fire down here, and then this beautiful green hillside up here. So we need those regions. Now I can see this green triangle has a base that's 4. This red triangle has a base that's 2, but what about the heights? Well, it's the height of the graph. This point is the point 2, minus 1. And this point is 8, 6. So that means that this red height is the number 1, and this green height is the number...
Wait, wouldn't it be 8, 4?
I made the same mistake in my last meeting. More stuff to show your parents. All right, so this height is 2. So I've got to do this area, stick a negative sign on it, and then this area, stick a plus sign on it, add them up, that'll be my area. So my signed area is going to be something with a minus sign plus something here. So that red area is going to be 1/2 the base times the height, and the green area is going to be 1/2 the base times the height. So minus 1 plus 4. So Signed area is 3. Coincidence or conspiracy? Same signed area we got before. All right, one more cool example. This will be up here. I'm sorry to be going so quickly. If I could do a chipmunk voice, it would be really good because I'm going really fast. The last page is another definite integral using geometry. The integral of square root of 25 minus the quantity x minus 6 squared, all that under square root from 6 to 11. So I don't really have time. This would be a great recitation problem where I wouldn't be up here giving it away. But here we go. We need to get to this so that I can let you get out of here on time. So I want to do some background here. How do we graph that? So question A. I want to get to this graph in stages. So here's an equation. X squared plus y squared equals 25. Raise your hand if you can tell me something about the graph that would go with that equation. Tell me one thing. Circle. Wonderful. Somebody else, tell me something else. Annika?
It's radius is squared.
Great. Somebody else.
Its center is the point 0, 0.
So the center is at 0, 0. So a picture of this circle would be this. Okay, what about this equation? X minus 6 quantity squared plus y squared equals 25. Somebody tell me what's changed in the graph. Oh, I thought your hand was going up. But do you know?
It's moving with the minus 6.
Okay, so tell me the result then.
It's moving down.
Oh, not quite, because the minus 6 is going with the x.
It's moving to the right 6, so the center point would be at 0, 6.
Yeah, so a circle, so r is still 5, and the center is at 6, 0. So that's going to look like this, 6, 0. Radius is 5. Oh, what's that point? 11, 0. And what's the other crossing? 1, 0. Because it's a radius 5 circle. Here's a cool one. There's an equation. Y equals 25 minus x minus 6 squared. What's the graph of that thing look like?
Looks like a parabola.
No. Jonah?
Would it be the same?
Oh, you can't ask me.
Is it the same?
You can't ask me. It's the same, yes. So what we mean by a graph is all the points that satisfy that equation. So all the points that satisfy that equation also satisfy this equation. It's the same graph. So there it is. Now, here we go. Everybody ready? Buckled in? How about this one? What's the graph of this?
Is it the same? It's the same?
Oh, it sounds like you're asking me.
No, it's the same.
You're wrong. Sorry. But why is that not the right answer? He said it's the same, but it's not quite the same.
Because the x minus 6 is still squared.
No, that's not it.
It's because it needs like plus minus, because you added the square.
No, this doesn't mean plus minus.
It's not square.
So this doesn't mean the same as this. This symbol means all the points that satisfy this and also satisfy one more condition. Y has to be greater than or equal to 0. So this symbol, a better word for this is the non-negative square root. So the things that satisfy that equation, it's the same, it's a portion of the same circle. So you weren't entirely wrong, but that's the graph. It's the top half of that circle. So again, to say that the point satisfies this equation means that it satisfies that equation and also satisfies the extra condition. Okay, so now what about our integral? We have to do the integral from x equals 6 to x equals 11 of this thing. Well, that means that we're looking at... Chris, is this why you asked me about the circle? Or were you on the other graph when you were asking about the circle area?
I was on the other one.
Okay. You can use geometry to find that area. Okay, so I'm not going to... Well, so the area, the signed area, is going to be pi r squared, but a quarter of that because you had to share with your siblings. So this is pi times 25 over 4. Isn't that cool? Yes, it's cool. It is beautiful. You get the craft of making these drawings is so satisfying. All right, so that was meeting part 3, and we have somehow I've been talking really quickly because we're ready for meeting part 4, which is short. We're going to run just a couple minutes late, but not. We started like 6 minutes late. I'm really sorry about that. Okay, so meeting part 4. Is kind of observations about what we've done. And then questions. And finally, a cliffhanger. So we have this new thing. We have this definite integral. So this is the definite integral. And what it's defined to mean is this thing. So you take the limit of this wacky thing. Really impressive. And all that is giving us is the signed area. Now, observation. So far, we've only done this in a couple of situations. We got an approximate answer using a computer on Monday. So on Monday, at the beginning of the hour today, where we were talking about the area under the graph of y equals 1 over x, and I said it was roughly 1.95. So we got an approximate answer using a computer, and then we got exact answers today using geometry. We didn't need all this theory for what we did today. We could have just used geometry to get those areas. That's what we did. So that's the observation about what we've done. So here's the question. Is there a way to get an exact answer without a computer? Is there a way to use analysis for a general function, not using geometry, not using a computer, get an exact answer? So to compute the value of the definite integral exactly, and I'm going to say analytically, by analyzing the things. So no computer, no geometry. Just your big math brain. So that's the question. So, good news. Yes. So there are some questions like this in section 5.1 and 5.2 where you do set up a summation like this, and you get a formula for what this thing actually represents. You take the limit of that and you get a number. So in book section 5.1 and 5.2. That's the good news. Bad news is that it's really hard. The book only presents some simple examples, the most basic functions, y equals x squared, y equals x cubed. So at the level of Math 2301, we're not even going to cover those in this class, I don't think. So Math 2301 level examples are hard and still are only the most basic functions. So, that was our question. So, next question. Then, is there a way that's not so hard? Is there a way to compute the value of the definite integral analytically, without using a computer, without using geometry, that gives you an exact answer, but is not so hard? Come back Friday. That's the cliffhanger. All right, thanks everybody. If you didn't sign in, please sign in now. So again, sorry to run late. Thank you.